Okay, in class we talked about this precipitation reaction and how we got here by swapping partners and then using solubility rules. So just for a quick review, we saw that silver nitrate is made with silver and nitrate, potassium sulfide with potassium and sulfide, and then our products will be silver sulfide and potassium nitrate, and that's what we have over here. And then we figured out that the silver sulfide is insoluble because of our solubility rules. We've got sulfides are typically insoluble and silver is not an exception. Okay, this way of writing the reaction is called the molecular equation. There's another way that's a little more realistic that is called the complete ionic. So it's more realistic in that it shows you how things are actually situated in the beaker. So in other words, the aqueous ionic compounds, because they're strong electrolytes, in reality they float around in the beaker as ions. So you have to explicitly write them all out, or it's useful to, and then we see what's really going on. So we've got the two silvers, the two nitrates, we've got two potassiums. Notice that the subscript becomes a coefficient because potassium makes a K plus. It doesn't make a K2 2 plus or something. And then you've got the sulfide. And on the right hand side, this solid really will just sit in the bottom of the beaker as one thing. So that stays together. It doesn't form ions. Then we distribute the two on the potassium nitrate. So two potassiums and two nitrates. So that's the complete ionic. It gives you a complete set of information. All the ions that are floating in there before, and then after, the solid that's formed and the ions that are still floating in there. There's another way to write this, which really just shows the change. So that's called the net ionic. So it's like when you get a paycheck, you have a gross pay, but then some things are deducted and you have your net pay, right? So that's really the change to your bank account then, is your net pay. And this will be the change in the beaker, the net chemistry that happens. So to get from the complete ionic to the net ionic, you simply cross off what's common to both sides. So here we have two nitrates on both sides, so those go. We have two potassiums on both sides, so those go. But the silver and the sulfide get together to make the silver sulfide. So your net ionic will just have that. Two silvers and a sulfide make the silver sulfide. And that's that for precipitation reactions. All right, let's do another example just for practice. So here I've got a Socrative question. Let's look at number 16. So what are the reactants for the complete ionic equation when Cu sulfate is added to sodium sulfide? You're going to need to memorize your solubility rules, but for now I'll put them there. So go ahead and pause the video and see if you can figure out which one of these is correct for what are the reactants for the complete ionic equation, just the reactants. All right, so I hope you pause the video so you can think about that. Let's go ahead and write them down. So we're going to have copper sulfate. So definitely we'll eliminate choice C and D because the sulfate won't fall apart like that. So Cu2 plus and SO4 2 minus. And then with the sodium sulfide, they're going to fall apart into sodium and sulfide. So the sodium doesn't stay together as Na2, 2+. So we'll have two sodiums and a sulfide. And then as far as solubility rules go, this makes sense that they'd be aqueous because sulfates are soluble and copper's not an exception. And sodium is soluble, no exceptions. All right, let's keep going then. So if those are the reactants, what would be the products? So go ahead and pause the video and see if you can come up with the products here. All right, so again, we're going to swap partners. So the copper is going to go with the sulfide, and the sodium is going to go with the sulfate. So we've got copper sulfide, so that's good. But not this sodium sulfate, so not A and not B, because the sodium's +1 and the sulfate's 2-. So we're going to need 2 sodium sulfates. So we're down to either C or D. Then we just need solubility rules. Well, sulfide is insoluble, typically, and copper's not an exception, so that should be a solid. So it must be choice C. Also, this works for as far as sodium goes because sodium is soluble, no exceptions, so it makes sense that that's sodium sulfate. All right, and then let's do one more. So then what's the net ionic equation? So we can go ahead and look at what we had before up here. So Cu2+ aqueous plus SO4 2- aqueous plus 2Na plus aqueous plus S2- aqueous. So that was just our answer from right here. And then what are our products? So the calcium with the sulfide we figured out is a solid, and then we're going to have 2Na plus aqueous and a SO4 2- aqueous. So from there you should be able to pretty easily figure out what the net ionic is. So pause the video and make your choice. All right, so we're going to cancel out what's common. So the sulfates go and the sodiums go. So we've just got copper and sulfide going to, sorry, I changed that to a calcium because of my poor penmanship. That should be copper and copper. All right, right on. So it would be this one. Okay, so that's it for precipitation reactions and examples. Now let's go ahead and look at another category of reaction, and that's acid-base. So for acid-base reactions, they're pretty similar to precipitation. But let's start with some definitions. So for simple acid/base neutralization, what are these things? So an acid is an H+ and an anion, and a base is a cation and a hydroxide. So now if you think about these two things, when they swap partners, the positive from the one, just like in precipitation, will go with the negative from the other. So that's H+ and OH-, and the positive from the other will go with the negative from the other. So a cation plus an anion. H+ and OH-, this will make water, right? H2O, and the charges cancel. the cation and the anion, this is called a salt. So I know in everyday life when we say salt, we think sodium chloride, but in chemistry, it's always the ionic product of an acid-base neutralization. And so in other words, acid, the reaction basically is acid plus base goes to water plus salt. Now let's look at an example. The typical example would be HCl is your acid, hydrochloric acid, that's aqueous, plus NaOH, sodium hydroxide, that's your base, and then of course water is H2O liquid. And let's figure out what the salt is. So looking at the ions present, swap partners, there's your water. The salt literally is sodium chloride in this case. So that's our molecular equation. It happens to be balanced because we're just making one water, one proton, one hydroxide makes one water. It's a 1-to-1 ratio. We could, again, just like we did with the precipitation reaction, write the complete ionic. The complete ionic is going to be all of the ions. So the H plus, the Cl minus, the Na plus, the OH minus, all that jazz. The water, we know water does not conduct electricity, pure water. So there's no ions there. It's a covalent compound, it's a non-electrolyte. But then the soluble salt, we know that salt does dissolve, and soluble salts are strong electrolytes, so there will be ions there. All right. And then, of course, we could do the net. For the net ionic, we cancel what's common to both sides. So in this case, it's just H plus. Those are gone. Plus OH minus goes to H2O. That's often the net ionic equation for an acid-base neutralization. And in particular, when the acid is strong and the base is strong, then this will be your net ionic equation. Let's look at an example with a weak acid and a weak base. So what if we have, well, let's do a weak acid and a strong base. So what if we have nitrous acid? So this one is weak with barium hydroxide, and that's strong. So again, actually I'm going to need to make a little room to balance here. Well, no, maybe not. Okay, anyway, let's think about what our ions are. So hidden in here are H plus and NO2 minus. Those really are our ions. I'll write them down, but be careful because this is weak, so it would be a dim light. So for the most part, the molecule stays together. But this is just notes to myself so I can see what I've got in there. And then I've got barium and I've got hydroxide. So I'm going to make water. I'm going to make barium nitrite. Those will be my products. So barium nitrite and water, salt and water. Okay, so this is not balanced. I need 2 nitrous acids, 2 waters. Oh, whoops. I need 2 nitrates because the nitrite is -1 and the barium is 2+. So I'm not using that 2 to balance it. I just forgot to put it in earlier. So that's my molecular equation. And then I can do my complete. So here's where a lot of students get it wrong. So like I've said, this is a weak acid. So weak acid means it's a weak electrolyte, it's a dim light. Most of the molecules stay together. So I treat this as a covalent compound. It stays together. Even though those ions are in there, it doesn't fall apart to ions the vast majority of the time. That's why it's a dim light. This is a strong electrolyte. So that one I'll break apart. Notice again, like before, the subscript comes up to be a coefficient. Here I have a soluble salt. This one isn't on your solubility table, so you'll just have to trust me that this is soluble. I wouldn't ask you to predict that on a quiz or a test. And then the waters. All right, now let's cancel what's common to both sides. And there really isn't much. It's just the barium. The bariums go away. And then the other thing you might notice, here I've got 2, 2, 2, 2. Since they're all multiplied by 2 now, for my net, I can cancel the 2's as well. So my net will be the weak acid plus the hydroxide react, and you end up with a nitrite. So basically the acid lost its H+, and the water. All right, let's do a Socrative example here. So what if we have number 19 on the bottom here? What if we have nitric acid, which is a strong acid, and calcium hydroxide, which is a strong base? See if you can predict the products. Pause the video, see if you can predict. All right, so what are your ions? So if you swap partners, you're going to make water and calcium nitrate. And you need 2 nitrates because it's a 2+ and a minus. So that's this choice. All right, that's it for acid-base. For molecular equations, complete ionic and net ionic equations, you should be able to do that part of your homework now.